Hey, OChemsters, this is Mrs. Vandelay, and I thought I would go over, this is page 13 in your notes, so we can go over it and you can see how I did these problems before you actually take your quiz today. So if you would get out your page 13 in your notes, hopefully you've already done them. It's easier if you have done them first than just to watch me do them. Let's see how it goes, okay? So first of all, the Lewis structure for these, carbon's in the middle. Carbon has 4 bonds always, you should know that. So it kind of looks like this, okay? So the shape, if you look, it has a coordination number of 4, 0 lone pair, so that will always be tetrahedral, okay? What about the polarity? Well, tetrahedral is usually typically symmetrical. However, what's different about this? So here I have a model, and I'm going to move my camera so it maybe looks a little better. So here's my model of carbon tetrachloride. All right, so if you look at the purple ones are your chlorine and the yellow one is the hydrogen. Even though there's no lone pairs on the carbon, okay, see, no lone pairs in the carbon, it is not perfectly symmetrical. You don't have the same bonds on each side, so I would say it is not symmetrical. All right, then also, do I have polar bonds? Well, the answer is I do have 3 chlorines. They don't cancel each other out. There is a dipole moment, so I do have polar bonds. I probably should put some like that. So yes, it is a polar molecule. So why is that important? Well, because we said earlier, today in these notes, that all molecules will always have London dispersion no matter what. If it is a polar molecule, you'll also have dipole-dipole. Now, do I have hydrogen bonding? No. What's hydrogen bonding? If you have a hydrogen attached to an N, O, or F, I don't even have an N or F, I have a Cl, so I do not have hydrogen bonding. But what about these diagrams? Now, before you panic, okay, you do not have to draw these pictures on your quiz today. Maybe your test next week, but not your quiz today, okay? But I still want to show you. So right here, if I hold my molecule kind of like this, if you'll notice, this end is where the chlorines are, and that's where your partial negative is. So then this side is your partial positive. Well, if I have another molecule here, let me move this over. Notice how I oriented this. My partial negative chlorines are lined up with my partial positive hydrogen of the other molecule. So there's an attraction between this area right here of the chlorines and the hydrogen of the other one, the partial negative of the chlorines and the partial positive of the other hydrogen. So how am I going to draw that? Well, I'm going to draw kind of small, I get it. So I'm going to do something like this, Cl, Cl, ClH. I'm going to do it again, Cl, 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 and I got the H. This is your partial negative, your partial positive, your partial negative, your partial positive. Why did I draw all that? Remember, we're talking about dipole, 2 poles, dipole, 2 more poles. So dipole, dipole. And let me get out maybe a red pen. Okay, so here is where the attraction is, okay, between the chlorine of the one, the chlorines of the one and the hydrogen of the other one. Let's keep going. How about the next one? Here's methane, okay, and I have a coordination number of 4. I have 0 lone pair. It is again tetrahedral, but what's different? Is it symmetrical? Yes, it is 100% symmetrical because no lone pairs and I have 4 of the same bonds, okay? Well, let me show you that. So here it is, perfectly symmetrical, 4 bonds, 4 atoms that are the same, no lone pairs. It is perfectly symmetrical. All right, and I really don't care at this point if it's symmetrical. I don't care about the bonds. Wake up. They're nonpolar anyway. I have a nonpolar molecule. So if I have a nonpolar molecule, what are my intermolecular forces? Only London dispersion and nothing else. So there's nothing to show. Okay, let me show you the next one. So here is the next one. This is your dimethyl ether. You'll know how to name that before this year is over. But anyway, this is what it looks like. Okay, So let's draw this, and I'm going to try to draw it to show you right here that it's bent in the middle. All right, so even though the carbons are tetrahedral, okay, it's bent in the middle. Okay, so I'm going to use as my central atom, the oxygen is bent. Okay, coordination number is 2 lone pairs. So then what? Is it symmetrical? The answer is no. Why not? Because I have 2 lone pairs on the oxygen, so it is not symmetrical. And what about the polarity? Well, if it's not symmetrical and I have an oxygen bond, so I have a polar bond, what does that tell you? It is a polar molecule. All right, I guess I'll spell it all out. It's a polar molecule. So what kind of forces do I have? I always have London dispersion. Why? Because they all have protons, they all have electrons, they all have London dispersions. But what else? Okay, well, I think it has dipole-dipole because it is a polar molecule. So does it have hydrogen bonding? Well, let's take a look. Here it is. I have an oxygen. I have these hydrogens. But is there a hydrogen attached to the oxygen? No, there is not. Hydrogen bonding only occurs when a hydrogen is attached to a nitrogen, oxygen, or fluorine. None of those are the case. So I do not have hydrogen bonding. And so how is this going to work? Well, I'm going to do it kind of like this. And I'm going to leave the hydrogens off because they're just going to make it messy. So this is my partially negative and my partially positive end. Well, I need a whole nother one because it's dipole-dipole. This is my partially negative, partially positive, and where is the attraction between the oxygen, the partial positive down here where the carbons are, and the partial negative of the oxygen. All right, well, what about the next one? Well, give me a second and I'll pull it up. Okay, so here is the molecule. I don't know if you can see it very well. Here's my CH3, C double bond O, so here's a double bond O right there, and then OH, okay? So CH3, C double bond O, OH, okay? So let me draw it out for you. And I need to put my lone pairs here, my lone pairs here, and then I need to put the H's there. So what about the shape? Well, I can call this carbon is trigonal planar. I hope you can read that. And this oxygen here is bent. Okay, so this is trigonal planar, this is bent. Well, just take a look at this molecule. What do you think? Is this symmetrical or not? It really doesn't look very symmetrical to me, so it's not symmetrical. How about polar bonds? Does it have any polar bonds? Definitely have 2 oxygens, definitely very polar. So this is a polar molecule. So I would maybe put it in a box like that. So now what? Better scooch this up a little bit, I guess. All right, so now what? What kind of intermolecular forces do I have? I always have London dispersion, always. It's polar, dipole, dipole. So now the question is there hydrogen bonding? Well, look at this molecule here. This oxygen doesn't have any hydrogens, but this one does. All right, so because there is a hydrogen directly attached to the oxygen, okay, there is hydrogen bonding. Okay, so what about the forces? All right, give me a second. I need a bigger piece of paper for this. All right, so I'm going to go back to the C double bond O, OH, okay, if I can just draw it like that. Actually, I should probably draw it a little bit different. Let me start again. So I have C double bond O, and now I'm trying to make that look bent. Oops, can't see that though, can you? There you go. Trying to make that look bent. So what is going to happen? Where is the attraction going to occur? It's going to occur between this hydrogen, this is a partial positive hydrogen, and here's your partial negative oxygen, and the oxygen on another molecule. So I want to do it like this, I'll do it like this, here's this, and here is this. Okay, so I just kind of redid it and put the bent oxygen over here. Why would I do it that way? Because here is where the hydrogen bonding attraction goes. So I'll say it again. It is the hydrogen that is attached to the oxygen on one molecule is attracted to the oxygen of the other molecule. That is hydrogen bonding. So like I said, don't panic. This is not on your quiz today. All right, maybe next week, but not today. But at least I'm showing you how this works. So I'll say this one more time. When you have hydrogen bonding, what's attracted to what? The hydrogen that's attached to the nitrogen, oxygen, or fluorine is attracted to the nitrogen, oxygen, or fluorine of the other molecule. Okay, so it is this hydrogen that's attracted to this oxygen. Okay, that is hydrogen bonding. So if you want to squeeze that in someplace, maybe put it down below. I really don't know. All right, so let's go ahead and do this last one, and then I'll be done. All right, so here is C2H5OH. So here's C2H5OH. Okay, and so let me draw that for you. I'll put my lone pairs on the oxygens. I will put all the bonds on my carbons, and there I go. So what do you think is the most important part of the shape here? Okay, it's probably right here. All right, this is the key. All right, so you can say carbon is tetra again, but it's the oxygen that's bent, and that's what makes this molecule polar. So because it's bent, it is not symmetrical. Because I have an oxygen, it is polar bonds. Therefore, the whole molecule is polar. I don't know if you can read that. Okay, so what does it have? London dispersion, dipole-dipole. Do I have hydrogen bonding? Well, take a look at this. Do I have a hydrogen directly attached to the oxygen? Yes, I do. So I have hydrogen bonding. All right, so how am I going to draw this? I'll try to draw this right here. Here's my partially negative, here's my partially positive. So now I need the HO and then my two carbons there. That's my partially positive. So it is right here. That's my hydrogen bonding occur. That's my attraction that's occurring. So again, the hydrogen that's attached to the O is attracted to the O of the other molecule. All right, and so that is hydrogen bonding. Okay, so hopefully if I asked you this information on your quiz, the first 4 columns, you'll do fine. Okay, you'll do fine. Oops, yeah, there we go. So if you don't have to worry about the pictures, you'll be in good shape. Okay, so now that you're done, you can go ahead and close your computers down, and you can get your quiz. So good luck, and we'll see you on Tuesday. Bye-bye.